To explain what partial fractions are all about, let's first consider the following. Let's say we have 1 over x minus 1 plus 1 over x plus 2. What we normally do here is to reduce the sum of these two fractions to a single fraction. So we find the lowest common denominator, and we can just simplify the numerators. Now we have 2x plus 1 over x minus 1 times x plus 2. Now what partial fractions involves is going from this step to that step there. So it's just the reverse, right? Here we're taking fractions and reducing them to a single fraction. Partial fractions involves taking that single fraction and splitting it up into the sum of two or more fractions. So that's the idea behind partial fractions. This form over here is more likely to be written like this, where the denominator is multiplied out. So it's going to be x squared plus x minus 2. So we have a rational function here. The numerator is generally called p of x. It's just a function of x. And the denominator is sometimes called q of x. So really we're looking for a rational expression of the same variable, p of x divided by q of x, whatever those they may be. They're both polynomials. We will now go from this fraction, and we can use partial fractions to now split this up into separate fractions. So the way that we do that is we first factorize, make sure that the denominator is in factorized form, which it is. So we have two linear expressions here, x minus 1 and x plus 2. So the one denominator will be x minus 1 and the other denominator will be x plus 2. Now because they are linear, we're just going to have a coefficient a constant term a and a constant term b, and that's all there is to it. So what we do now is we take the right hand side and we just express it as a single fraction. So we'll have a times x plus 2 plus b times x minus 1, and then we equate it to the left hand side. And the idea behind partial fractions now is to compare the numerators. The denominators are equal, so the numerators have to be equal. So we're comparing the coefficients of each term on the left to those on the right. So we're going to take the coefficient of x first, which is 2 on the left, and we're looking at the coefficient of x throughout on the right. So we have a times x, so we have one coefficient there of a, and then b times x, so we'll have plus b as well. So we've got one equation here, a equals 2 minus b. And likewise, we can look at the constant term on both sides of the equation. So 1 equals, the constant term here will be 2 times a, 2a, and then b times minus 1, so minus b. So b equals 2a minus 1. We can now solve for a and b using simultaneous equations. So a equals 2 minus b, which is 2a minus 1. A equals 2 minus 2a plus 1. Take that across there. So 3a equals 3 and a equals 1. A equals 2 minus b. Let's just write we've got b here. So b equals 2 times 1 minus 1. So b equals 1. So a and b are both 1. So this will be 1 over x minus 1 plus 1 over x plus 2. And that's what we started off with when we introduced partial fractions. So that's the idea behind partial fractions. Before we go through some examples, I just want to go through a couple of scenarios that you're likely to come across. As you'll see, I've neglected to put the numerator in over here because the essence of partial fractions has everything to do with the makeup of the denominator. So the first example, we're looking at linear expressions. X plus 1 is linear, and so is x minus 2. Now note that the denominators must be in factorized form or factored form before we can then decompose into partial fractions. So when we have linear expressions, we've got two linear denominators here, so which means we have two fractions. So one fraction will have a denominator of x plus 1, and the other fraction will have a denominator of x minus 2. Now, because with a linear denominator, we're just going to have a constant term in the numerator, such as a. And similarly, for the second fraction that has a linear denominator, we're going to have a constant term in its numerator. When it comes to the second example, we have a linear expression, x plus 1. Now, x minus 2 all squared may look like it's quadratic. It's a quadratic expression when you multiply it out, but in factored form, it's a linear expression written out twice, right? So essentially, it's x plus 1 times x minus 2 times x minus 2. So it's really the linear expression written out twice. So we will have the first fraction will be x plus 1. The second fraction will be just one instance of that linear expression. So it will be x minus 2. And then we have to include a third fraction with the denominator x minus 2 all squared. The reason being, when you take two fractions, if we just ignore the x plus 1, the first fraction for now, when we find an LCD between x minus 2 and x minus 2 all squared, the LCD is x minus 2 all squared, which is what that is over there. But you need to account for it when decomposing into partial fractions. So x plus 1 is linear, the numerator will be a constant term. X minus 2 is linear, the numerator will be a constant term. X minus 2 is linear, again, the numerator will just be a constant term. However, what's different with number 3, x plus 1 obviously is linear, but x squared plus 2x plus 4, it is quadratic, it cannot be factorized, hence we cannot put it into factor form. So we will have two fractions. The first fraction has a denominator of x plus 1, and the second fraction has the denominator, the quadratic denominator, x squared plus 2x plus 4. The linear expression, the denominator is linear, so the numerator is a constant term, a. The second fraction has a quadratic denominator. So we now need to account for an additional variable in the numerator, so it's bx plus c. So what you need to notice is that we look at the degree of each denominator, and the numerator will be 1 less than the degree of the denominator. So in other words, if the denominator is a linear expression, the numerator will be a constant term. If the denominator is a quadratic expression, then the numerator will be a linear expression. We very rarely get cubic expressions in the denominator because they can, in most cases, be expressed as a linear expression times a quadratic expression. So that's the route that you would normally take. However, in the event that you cannot do that and you need a cubic expression in the denominator, then your numerator will be a quadratic expression. And that's the idea behind partial fractions. Okay, so the first thing we do here is we're going to factorize the denominator. So 13 minus x over x1 5 plus minus. So this is now, we have two linear expressions here. So again, we are going to have the first denominator being x minus 1 and the second denominator x plus 5. And because they're linear, we're just going to have an a and a b. So now we're going to take this on the right hand side and reduce it to a single fraction. So we'll have 13 minus x over x minus 1 times x plus 5 equals a over x minus 1 plus b over x plus 5, and that equals, just reducing that to a single fraction by finding a lowest common denominator, a times x plus 5 plus b times x minus 1. Okay, we're now going to compare the coefficients in the numerators on both sides. So we'll start with the constant term here. So we have 13 equals. The constant term here will be 5 times a. So we have 5a and b times minus 1. So b equals 5a minus 13. And then the coefficient of x will be minus 1 on the left. And then we have a times x. So we have a and then b times x plus b. So minus 1 equals a plus b, which is 5a minus 13. So we'll take that across there and we'll get 12 equals 6a, a equals 2, and b equals 5a. So it's 5 times 2 minus 13. 10 minus 13 is minus 3. So a is 2 and b is minus 3. So we're just going to write this as 2 over x minus 1 minus 3 over x plus 5. You should always just check the work as well. So we're just going to reduce the right hand side to a single fraction. So it's 2 times x plus 5 minus 3 times x minus 1. And all we're concerned about is the numerator, right? So it has to equal 13 minus x. The numerator must equal 13 minus x. Just multiplying out the numerator on the right will give us 2x plus 10 minus 3x plus 3. And that'll be 10 plus 3 is 13. 2x minus 3x is minus x. And that's exactly what we have over there. Here, our denominator is already in factorized form, so we can just split it up. Each of these are linear expressions, right? So we're going to have a over x plus 2 plus b over x plus 2 squared plus c over x minus 4. Each linear factor, if we just write this out, expand this, each linear factor must appear in our denominators, right? Every single possibility. So we've got x plus 2, which appears here, but we also need to include x plus 2 all squared. We need that part, that denominator as well. Because when you're finding an LCD, you will have an the LCD between x plus 2 and x plus 2 all squared is x plus 2 all squared. It's the first quantity that both will divide into, right? So you have to include x plus 2 and x plus 2 all squared, and then obviously the third factor, x minus 4. So we've got a over x plus 2 plus b over x plus 2 all squared plus c over x minus 4. So when we get a single fraction out of this, we'll have the denominator, the LCD is x plus 2 all squared times x minus 4. And then we'll have a times x plus 2 times x minus 4 plus b times x minus 4 plus c times x plus 2 all squared, and that equals x squared plus 6x minus 4 over x plus 2 all squared times x minus 4. Now all we need to do is equate the coefficients. So what we're going to do, we're going to ignore the denominator now. Just going to rewrite the numerators out by multiplying these brackets out. So x squared minus 2x minus 8 plus b times x minus 4 plus c times x squared plus 4x plus 4. So we're going to compare the coefficients of x squared first. So we'll start off with 1. 1 is the coefficient of x squared on the left. Then we have a and plus c. Right, so there's one equation. We're going to compare the coefficients of x. So we'll have 6 equals a times minus 2x. So we'll have minus 2a. B times x plus b. And then c times 4x. So we'll have plus 4c. There's the second equation. Because we have 3 variables, we need 3 equations. So the last one will take the constant term and just equate all the constant terms. So a times minus 8 is minus 8a. B times minus 4 minus 4b. C times 4 plus 4c. And there is the third equation. Now we just have to solve them simultaneously. Okay, so from the first equation, a equals 1 minus c. So we'll have 6 equals minus 2 times 1 minus c plus b plus 4c. 6 equals minus 2 plus 2c plus b plus 4c. So we'll have 8 equals 6c plus b, or b equals 8 minus 6c. Okay, and then we have minus 4 equals minus 8a, so minus 8 times 1 minus c, minus 4 times b, so that's minus 4 times 8 minus 6c plus 4c. Okay, so we have 8c plus 24c is 32, c plus 4c is 36c. And then we have minus 8 minus 32 is minus 40. Take that across. 40 minus 4 is 36. So c equals 1. Okay, so a will be 1 minus c, 1 minus 1. So a equals 0. B equals 8 minus 6 times 1. So b will be 2, and then obviously c is 1. So partial fractions, I will have 0 over x plus 2 plus 2 over x plus 2 all squared plus 1 over x minus 4. So we can take that one out. And that's the partial fraction. Now we're going to check that this is correct, as you always should. You should always check your work. So on the left, on the right, we have x plus 2 all squared times x minus 4. That's the LCD. And we have 2 times x minus 4 plus x plus 2 all squared. We're not going to bother with the denominator. We're just going to multiply out the numerator to check that we get this expression here. So that'll be 2x minus 8 plus x squared plus 4x plus 4, which is x squared plus 6x minus 4, which equals that numerator over there. So the answer is correct. So this is how you would rearrange that into partial fractions. So now here we have a linear expression x and a quadratic expression x squared plus 5. So we will have a over x, that's for the linear expression. But for the quadratic, we need to add another variable in the numerator. So we have bx plus c over x squared plus 5. So the denominator is x times x squared plus 5. And we have a times x squared plus 5 plus x times bx plus c. Again, we just compare the numerators. So we're going to look at the x squared terms first. The coefficient of x squared on the left will be 12. And then we have a plus b. And then the constant term, we've only got two variables, and sorry, we have three variables. We're going to need a third equation. So the second equation, we're looking at the constant term 20. So we'll have a times 5. So we'll have 5a. And we don't have a constant here because every term will have an x in it, right? So a will be 4, which is nice. So 12 equals 4 plus b. So b equals 8. Okay, we'll let x be 1. Just to formulate the third equation, take any value of x that works. 0 wouldn't work because if x was 0, then you'd have 20 equals, that would be 0. So you'd have 5a, and then this whole term would be 0. So you'd have 5a equals 20. You'd just get back to a equals 4. So that x equals 0 is not going to help. So try x equals 1. 12 times 1 squared is 12 plus 20 is 32. 1 squared plus 5 will be 6, so we'll have 6a. And then that'll be 1 times b plus c. So 32 equals 6 times 4, 24, plus 8 plus c. So c will be, that's 32, so c is going to be 0. Okay, so we will have a is 4, b is 8, and c is 0. So this whole numerator will be 8x. So let's just check that now. So we'll put 4 times x squared plus 5. We're just checking it in here. Plus x times, and b is 8. So it's going to be 8x and c 0. So we'll have 4x squared plus 20 plus 8x squared, which is 12x squared plus 20, and that is our numerator. So this is the partial fraction decomposition. Okay, whenever we have an expression in the numerator that is of an equal or greater degree than that in the denominator, we're going to have to use polynomial division to find a remainder before we can then decompose into partial fractions. So in other words, if p of x is 3x squared plus x minus 17, and q of x is x squared minus x minus 12, then when we divide q of x into p of x, we're going to get a quotient at the top, and after all of this, we are going to get a remainder r of x, which is then used to then decompose this fraction. So we are going to divide x squared minus x minus 12 into 3x squared plus x minus 17. X squared goes into 3x squared 3 times. We then multiply 3 by x squared, and that's the first term here. 3 by minus x, so we have minus 3x, and 3 times minus 12 is minus 36. And now we subtract the bottom terms from the top terms. So 3x squared minus 3x squared is 0. Plus x minus minus 3x is plus x plus 3x, which is 4x. Minus 17 minus minus 36 is minus 17 plus 36, which is plus 19. This expression here, we cannot divide this expression x squared minus x minus 12 into this expression 4x plus 19, because 4x plus 19 is of a lesser degree than x squared minus x minus 12. So this is our remainder, r of x. So in other words, this expression here, 3x squared plus x minus 17 divided by x squared minus x minus 12 equals 3, which is our quotient here, plus, and then we have the remainder, 4x plus 19 over x squared minus x minus 12. So only when we have the numerator of a lesser degree than that of the denominator can we immediately move into partial fractions. So we're now going to take this expression here and decompose into partial fractions. So 4x plus 19 over x squared minus x minus 12. We just need to factorize that denominator first. So x and x, 3 and 4 minus and plus. So this will equal a over, these are both linear expressions. So we have a over x plus 3 plus b over x minus 4, and we can proceed as we did before. So we have a times x minus 4 plus b times x plus 3, and that equals 4x plus 19 over x plus 3 times x minus 4. Now, as before, we compare the coefficients. We've got two variables here, we need two equations. So we'll first start with the coefficient of x. So we'll have 4 on the left, and then we have a plus b. And then the constant term is 19, so 19 equals 8 times minus 4, so minus 4a, and b times 3 plus 3b. So a equals 4 minus b. The 19 equals minus 4 times 4 minus b plus 3b. 19 equals minus 16 plus 4b plus 3b. 35 equals 7b, and therefore b equals 5. A equals 4 minus b, so a will be 4 minus 5 is minus 1. So we'll have minus 1 over x plus 3 plus 5 over x minus 4. And we can verify this, check it before we continue. So we'll have our denominator, and the numerator will be minus x minus 4 plus 5 times x plus 3. We're just going to multiply out the numerator here. Minus x plus 4 plus 5x plus 15. That'll give us 4x plus 19, which is what we have here. So everything checks out. Right, so this part here is just that. Remember that we need to add 3 because 3 was our quotient. So 3x squared plus x minus 17 over x squared minus x minus 12 equals 3 plus all of this. So it'll be minus 1 over x plus 3 plus 5 over x minus 4, and those are our partial fractions.